Nitric 5 acid. In the laboratory, nitric 5 acid is prepared by the reaction of concentrated sulfuric 6 acid with a nitrate. Potassium nitrate is commonly used because it does not contain any water of crystallization. The setup for this experiment is given here. When a mixture of potassium nitrate and concentrated sulfuric 6 acid are heated, they react to form nitric acid according to this equation. However, some nitrogen 4 oxide is produced and it appears as brown fumes. It is important to have an all-glass apparatus because nitric 5 acid fumes attack cork, rubber, or any other organic compound. Now the nitric acid formed will actually form first of all in form of fumes that will be mixed with the brown fumes of nitrogen 4 oxide. The mixture of fumes is taken into the collection flask where it is cooled and will remain with the nitric acid. The nitric acid formed through this process will appear yellow because of the impurities of nitrogen 4 oxide. In this equation, you notice that the salt formed is potassium hydrogen sulfate. Now, potassium sulfate is not formed because it would require higher temperatures that cannot be achieved in the laboratory for this setup.
Laboratory preparation of nitric acid. Shown here is the arrangement for the preparation of nitric acid in the laboratory. A mixture of equal parts by weight of sodium nitrate and concentrated sulfuric acid is heated gently in the retort. Nitric acid formed being volatile distills over. The concentrated nitric acid vapors are collected in a water-cooled receiver. The vapors are condensed into a liquid gradually.
Ostwald's process. Here we have 4 chambers, namely catalyst chamber, cooling tower, oxidizing chamber, and absorption tower. A mixture of pure dry ammonia gas and dry dust-free air in the ratio of 1:10 is fed into the catalyst chamber. In the presence of the platinum gauze at 700 degrees Celsius to 800 degrees Celsius, the ammonia is oxidized to nitric oxide. This is an exothermic reaction. This nitric oxide gas is allowed to pass through the cooling tower, and the gas is cooled to 50 degrees Celsius. The cooled nitric oxide is now allowed to pass into the oxidizing chamber. This chamber has an inlet for fresh oxygen. Here, nitric oxide combines with oxygen to forming nitrogen dioxide. 2 molecules of NO plus 1 molecule of O2 gives 2 molecules of NO2. That is nitrogen dioxide. This nitrogen dioxide and non-reacted oxygen then flows into the absorption tower, which is a stainless steel tower packed with acid-resistant quartz. Here, water is sprinkled from the top, so it slowly trickles to the layer of quartz. The water dissolves with nitrogen dioxide and non-reacted oxygen to give dilute nitric acid. 4 molecules of NO2 and 2 molecules of H2O and 1 molecule of O2 gives 4 molecules of HNO3. Dilute nitric acid can be synthesized from ammonia via the Ostwald's process. A mixture of ammonia and air is passed through a catalyst chamber where ammonia is oxidized to nitric oxide. This nitric oxide is passed to the cooling chamber where it gets cooled and then enters the oxidization chamber, which is connected to an oxygen inlet. Here, nitric oxide combines with oxygen, forming nitrogen dioxide. This nitrogen dioxide is allowed to pass through the absorption tower, where the nitrogen dioxide is dissolved by water, forming dilute nitric acid.
To summarize the large-scale manufacture of nitric acid, we'll use some equations. The key equations: as the raw materials are oxygen and ammonia, ammonia is oxidized in the presence of platinum catalysts to give nitrogen 2 oxide and water. The nitrogen 2 oxide produced is oxidized by the remaining amount of oxygen to form nitrogen 4 oxide. The nitrogen 4 oxide is then taken to another chamber where water is added to it to form a mixture of nitric 3 acid and nitric 5 acid. The nitric 3 acid is further oxidized to nitric 5 acid. The yield of nitric 5 acid in this process is about 65%, which means that the nitric 5 acid produced in the industry is 65% and the rest is water. Some common reactions of dilute nitric acid include: dilute nitric acid reacts with carbonates to form a salt, water, and carbon 4 oxide, just like any other typical acid, according to these equations. They also react with hydrogen carbonates to form similar products, like in the equation of sodium hydrogen carbonate and nitric acid, to form sodium nitrate, carbon 4 oxide, and water. Dilute nitric 5 acid reacts with a base or bases to form a salt and water only. This is also another typical reaction between acid and bases. Reactions of concentrated nitric acid. Since we looked at the reactions of dilute nitric acid and we found that it behaves just like a typical acid, the concentrated acid behaves in a different way. Firstly, concentrated nitric acid is a strong oxidizing agent, and it oxidizes iron 2 salts to iron 3 salts, while itself is reduced to nitrogen 2 oxide. For instance, when concentrated nitric acid is added to acidified iron 2 sulfate, which is green in color, it would turn yellow which would mean it has formed iron 3 sulfate. Now the dilute sulfuric acid here is the one that is used to acidify the iron 2 sulfate. The other products include nitrogen 2 oxide gas and water. Nitrogen 2 oxide is readily oxidized to form nitrogen 4 oxide, which is seen as brown fumes rising from the test tube. Since we have already said that concentrated nitric 5 acid is a strong oxidizing agent, it oxidizes sulfur to sulfuric 6 acid, while itself is reduced to nitrogen 4 oxide. When sulfur reacts with the concentrated nitric acid, it will form sulfuric 6 acid, nitrogen 4 oxide, and water. Copper is also oxidized to copper 2 nitrate, while nitric 5 acid is reduced to nitrogen 4 oxide and water. And this is the reaction that we utilized in the preparation of nitrogen 4 oxide gas. The uses of nitric 5 acid. Nitric 5 acid is used in the purification of metals such as silver and gold. It is used for etching designs on some metals. It is used in the manufacture of dyes and drugs. Some of the dyes you can see here. Another use of nitric 5 acid is in the manufacture of nitrogenous fertilizers, in the manufacture of explosives such as TNT, even though TNT was banned.